Hi, my name is Scott Simpson, and today we'll be talking about integrated rate laws. So far, we've discussed how to determine a rate law, but we haven't discussed how to actually figure out what the concentration of a product or a reactant is over a certain amount of time. So you can do that with these things called integrated rate laws. So integrated rate laws can be used to determine amounts of products or reactants over time. Okay. So how is that done? Well, let's consider a first order reaction. So consider the following first order reaction. So if we're talking an overall first order reaction, we have rate is equal to our rate constant times A, and since it's first order, it's to the power of 1. Now, let's say we consider the disappearance of A with respect to time. So if we could pick different portions to be our rate, but if we consider the rate of disappearance of A, with respect to time. Then we're going to change our rate a little bit. We're going to use some calculus. So we have the change in A with respect to time is equal to negative K. A. So we know that the concentration of A should be becoming less or more negative as time goes on, assuming A is a reactant. So it's negative due to the rate of disappearance because the species is disappearing. Okay, so now let's isolate all the A terms on one side and all the T terms on the other side. So to do that, we got to manipulate A over, so we get dA over concentration of A, and let's move time over to the other side. So we get K times dt. Okay, and the whole point of this was to determine the concentration of a reactant at some point in time later on. So if we want to do that, we have to integrate this expression. So now, to determine the concentration of A at some time t, we have to integrate both sides. So on this side of our integration, we need a point at which we're starting with an initial amount of A, so an initial concentration of A. So we'll call that A naught, or A 0. And we're going to go to some concentration of A at a later time, the time that we care about. And we'll call that A sub t. A all over A is equal to the integration of, okay, so now we're considering t. So we have our initial time of t is equal to 0, and we're going to go to some point later on, t, minus k dt. Okay. These integrals are easy to solve. They're from your calculus class or Calc 2 class. We know 1 over x should get us an ln of x. So what ends up happening is we get ln A at some time t minus ln of A naught is equal to, this side's pretty easy, so we can pull the negative k out. We get to our upper limit t, so the derivative of, or the integral of 1 with respect to whatever variable we're looking at should just be that variable. So in this case, we have dt. So if we integrate, we get t minus 0. Okay, cleaning this up a little bit, we get ln A t minus ln of our initial concentration of A minus k times t. And again, we were interested in this, this variable here, or this concentration of A at a certain time. So let's rearrange this to solve for ln of AT. It's equal to, so we get negative K times T plus, so we've moved this term over, ln of A naught. Okay, so this is a more useful form of this expression. How does that really benefit us? Well, if you investigate this, this is what we're looking for. This is what we're keeping track of. This is actually an equation of a line. So this is y is equal to m times x plus b. Okay, so this is an equation of a line. So you can have other orders of reactions, 0, first, second, third, and so on. So what do those integrated rate laws look like? Well, in general chemistry, we tend to really only consider 0 to 2. So let's make a table of those. So what we're going to do is we're going to keep track of the order of the reaction. We're going to have the integrated rate law. And we're going to keep track of the slope. Okay, so we have 0th, first, and second. For the integrated rate law for a 0th order, it happens to be AT is equal to negative K times T plus our initial concentration of A. Looking at this, again, keeping this in the form of y is equal to mx plus b, our slope will then be negative K. First order we already did. We had ln of A T is equal to negative K times T plus ln of the initial concentration of A. And we set our slope right up here was just negative K. For the second order, it ends up being 1 over A at our time that we're interested in is equal to K times T plus 1 over A naught. And in this case, looking at this, we can see our slope is equal to positive K. Okay, so now we have these integrated rate laws, but how do we determine what's the concentration of A at a certain amount of time, or what's the order with respect to A given a certain reaction? So question, how do we measure, or how do we determine the order of a reaction? So how do we do this experimentally? Well, the first thing we need to do, you need to measure the concentration of whatever you're looking at. Okay. In some cases, this could be done through Beer's law. You're measuring the adsorbance and you can relate it to concentration. There are other methods to do this. And then you want to measure this concentration, what happens to it with respect to time. So you're keeping track of the concentration and you're keeping track of time. 2, then what you want to do is after you measure that data, you want to make a plot. You want to make a handful of plots. You want to get the concentration of A versus time. You want the natural log of the concentration versus time. And you want 1 over the concentration versus time. Now, why are you doing that? Well, you're trying to fit this data to these different integrated rate laws up here. So this will be for the 0th. This will check to see if it is a first order, and this final one will check to see if it's a second order. Okay, and then what do you do afterwards? You pick the most linear plot of these plots. Most linear plot. and that tells you the order. Okay, so as an example, let's look at a quick graphical example. Given the following plots, what is the order of the reaction with respect to B? So B is a reactant. We're going to have the following plots. We have concentration of B versus time. We'll have time, and then we'll have ln of B, and then we have 1 over B with respect to time. And these are the 3 plots we get. So now we have to investigate these. We'll pretend that we already collected our data, we've made these plots. The last step, we have to pick the most linear plot. And looking at these plots, I would consider the first one the most linear. So I would say that this one is the most linear. Therefore, the rate, or the order of the reaction with respect to B is 0th. So that's how you determine what is the order of a reactant with respect to time. If you have any questions or comments, I would be happy to answer them. Please leave a comment below or feel free to email me. Thank you very much.